We've talked about solids a lot. We talked about crystals. We talked about polycrystals. We've talked about amorphous materials. We're going to get into some specific types of materials, namely ceramics and polymers. We're just going to mention metallic materials really quickly. Metals are made up of metallic atoms. They have very simple structures. They aren't molecules. They're atoms which are spherical. They crystallize very, very easily. So we're really not going to talk too much about them right now. We've talked about crystals, and so the idea of if we understand crystals, then we're going to understand much about metallic materials right now. So we're going to jump into ceramics, and we're going to go through these pretty quickly. This isn't meant to be a full discourse on all these. There are actually whole classes that you can talk about ceramics and polymers in. All right, so ceramics are also called ionic solids. In this case, for ceramics, each lattice site contains a pair of ions, not just a single atom like a metal would. An ion is a charged atom. We have positively charged and negatively charged, namely anions and cations. And usually anions are larger than the cations, and that's because there are more electrons. So these ions are going to assemble to maximize the attractive forces and minimize repulsive forces. We talked about that when we discussed bonding. And so what we want to do is we want to get into a little bit of stoichiometry. That's a very, very important part of ceramics. We're not going to get into it a whole lot. But what we need to do is we need to just make sure that our picture, or that the anions and the cations that we're using are going to show what that the charges are going to equal out. Sorry. Because we're dealing with charges here, we need to make sure that our positive and negatives equal out. The way they bond is going to work and everything. We can't have a charged crystal. The crystal itself has to be neutrally charged. So sorry about that. For just going to step back here. I want to talk about how these are going to assemble real quick. The cations and anions are going to be attracted to each other, and so these are going to want to pull together. But also what's going to happen is as they pull together, these two blue ones here, which have the same charge, are going to start repelling. They're not going to want to get so close. And also, the green ones are going to be getting closer together, and they're going to try to repel. And so it's kind of this dance between, where do we want to sit? And this is just in 2 dimensions. So in 3 dimensions, it's going to be quite a bit different. There's a lot more going on there. I do have this rule, a little bit about the stoichiometry and some other things. We're going to say that the cations are going to occupy the largest available site. And so we have that the radius of the site is going to be equal or less than the radius of the cation. And this is only going to be up to some limit. And this happens because they're going to start feeling each other. All right, let me draw this out because that in and of itself might not make as much sense. So I'm going to have a big red circle be my anion. And I'm going to make a small green circle be my cation. All right, so if I have my cation here, and if I have my anions come in and they're too big, all right, let's say that they are too big. Keep hitting the wrong button here. All right, I'm going to actually draw my anions first to make sure that this works the way I want. So here are my anions, and if I were to put a cation in here, and it was too small, it wouldn't quite fit in here, we would say that this is unstable. And I think we can see why it would be unstable, because I have the anions touching other anions, and they're the same charge, and so they're not going to want to be attracted to each other. So why would they want to attract to touch if they can't get very close to the cation? We can have a different picture. Let's say that I have a larger cation and or smaller anions. We would say that this one is stable. The charges, everything's happy. Positive is only touching negative charge things. There's a gap between like charges. If I were to continue drawing this out, I would have more cations filling in these gaps with more anions spaced plenty away. There is going to be a spot right in the middle that we're going to call the stability limit. And the stability limit is where we go from stable to unstable. Basically, let's say that these charges or these equally charged ions are actually touching each other. The anions are touching, but it's also touching the cation in the middle. That would be our stability limit. All right, so that's just a little bit. We'll actually look at some pictures here in a second to kind of get a better idea of that. I do really quickly just want to mention an example here about the lattice structure, and that is going to be for NaCl. It's face-centered cubic. It's got a rock salt structure. And I'm going to try to draw this as carefully as possible. Now remember, a face-centered cubic, it's going to have an atom on any given face. And so what we want to look at here is I'm actually going to draw this two ways. I'm going to go ahead and draw the second one really quick. There are two ways to think about this. So I could say that it's going to do this. I could say that I have, it doesn't matter which one this one is. I have the red one. Let's say that's my sodium. And I'm going to have that on my face as well because this is face-centered cubic. So where then are my chlorines going to be? Chlorines I'm going to put on my edges. So initially, I said it was face-centered cubic, and it looked like face-centered until I started adding in these blue ones here. And now it doesn't really look like face-centered cubic, it looks like it's more. Now I'm going to jump over to this other one really quick, this other picture that I'm going to draw. We'll talk about the second picture first. I'm going to, just off to the side of each corner, I'm going to put my sodium, and I'm going to then put my chlorine right at the exact same spot, or at least right next to it. And so when we talk about, and if I scroll up to the top, let's see, where is it? Each lattice site contains an ion pair. And that's the picture that I drew here. So each lattice site, so this corner has an ion pair, this corner has an ion pair, each face has an ion pair. Now, it's an easy way to mention that we basically have to have pairs so that we have neutral charges. When we talk about ceramics, when we talk about ionic materials, but in reality, we know that they're not going to be nice and spaced out this way. So what actually is happening is a picture that is closer to what we have here. And in this picture, I have a positively charged ion on the corner, and its negatively charged ion, its pair, we've bumped over into the middle so that it's equidistant between these two positive charges. So what I've really done here is, if I wanted to, I could extend out my unit cell just a little bit, just a half unit out. And in the next unit cell over, we would have something that looks like this. And so we have a pair here, 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 we have a pair. Everything has a pair. So in this case, the case on the right, we can easily see that we have an NaCl pair at each lattice site. But what it really is doing, and what it really looks like, is we have two FCC superimposed lattices. That are shifted just half a unit over. So if we kind of just let's ignore the blue ones for now. If we just ignore the blue dots and I look at this original one, I have an FCC. I have red at each corner and I have a red at each face. If I then ignore the red ones and I look at my dotted line box here, we have at each corner, we have a blue, and we have a blue at each face as well. So we basically just have two superimposed lattices. All right, so what can we do? Mathematically, what we can do is, to determine this structure a little bit better, is we can just take a simple ratio of the ion radiuses that are used. And so we do the cation radius divided by the anion radius, and we're going to get some ratio. Now, be very, 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 very careful here. Make sure you are using radius of the cation and anion. They're going to be significantly different than the radius for just an atom that is neutrally charged. So make sure that you are getting the cation and anion radiuses when you plug this in. I looked this up, and depending on the chart, of course, the numbers can be slightly different. I went ahead and plugged those in, and I got about 0.695 for my radius. What I can do then is I can go to this chart below, and I have this coordination number chart, and I'm going to try to find where this number fits in. And this number fits in between here. So it's in between 0.414 and 0.732. And so what I have here is I have a coordination number of 6. Now what the coordination number really is saying is how many nearest neighbors does it have that are of an opposite charge. And so if it falls between the range of 0.414 and 0.732, it's going to have 6 nearest neighbors of an opposite charge, and it's going to form an octahedral type pattern. And so this is what it would end up looking like. And then of course I could repeat this over and over and over again like we do with our other crystal structures. Really quickly, we're going to go through polymers. Now polymers, there's a lot of stuff here, and we are going to go through it really quickly. We can talk about it more if you want to get into polymers, but we're really just going to hit some things. We're going to go through this really quick, and there's a ton of stuff that we're going to talk about. So first off, polymers mean many units, and these many units are joined together into a large molecule. There are carbon usually hydrogen, and then there can be other atoms, and they're all covalently bonded together into these long chains, and these long chains are then attracted together from the sides by van der Waals. So really quickly, if I were to just sketch, I would have a bunch of stuff happening over here, and then, because I'm just drawing a small segment of this long polymer chain, I have a carbon, it's bound to a carbon, it's bound to a carbon, it's bound to a carbon, and so forth, and it just keeps happening like that. What we're going to see, though, is off to the side, because remember, carbon is going to be able to have multiple bonds. In this case, it's going to have 4 bonds. 2 of them are used up just by bonding to neighboring carbons, but the other bonds are going to be something else. And right now I'm just going to put an R here, but they can be really any molecule or any atom that it can bond to. Sometimes they're simply just a hydrogen. So this is one way to do it. It's a 2-dimensional drawing of what's happening here. There's another way to do it, and that is we can just, I'm going to try to make those a little bit more crisp. Nice corners. And what it is at the end points, so on both ends and at these peaks and valleys at the corners, what it is there's a carbon sitting at each one of those. It's just shorthand. So really there's a carbon right here, there's a carbon right here, there's a carbon here, here. That way I don't have to draw out all my C's. Also shorthand is if they're simply just hydrogens that are sitting attached to each carbon, I can just leave it blank. There's nothing else I have to do. We just understand that there are going to be 2 hydrogens there. But there could be other things bonded here that are maybe not hydrogens. And so that's something to keep in mind as well. So these are attracted together. We're going to go through a couple different ways to do that. Number 1, we have thermoplastics. Thermoplastics are polymers that can be heated, reheated, remolded, cooled multiple times. There's very little cross-linking, which we'll get to in just a second. Properties of this is they're ductile, they're flexible, and they get soft when heated. Examples of this is normally things that we think about when we talk about plastic, grocery bags, bottles, things that you can recycle. And so if I have a polymer chain, and I have another polymer chain that nears it, gets by it, because again, these are just long, one-dimensional molecules for the most part. They're really long in one direction, and when I say long, they can get very long, thousands, millions, billions of units long. And when they get close to another chain, even if it's its own chain folding back in on itself, there's going to be some attraction here. And these attractions are going to be van der Waals. This is a linear chain. Linear attraction. Basically, we have these long linear chains and they're attracted to each other. We could have a branched polymer. And a branched polymer is very similar, but what I have is maybe something where I have a branch and another polymer comes off of it. And again, I could have another one over here, and maybe it has some branch as well. So there's some branching going on. In this case, it's still going to be held together with van der Waals forces as it gets close to other polymer chains. So some examples of this would be if you've ever looked at some plastics, if you've ever recycled some plastics, maybe you've heard of HDPE. That is high density polyethylene. That's what the HD is for, is high density. The branched one, an example of that would be LDPE, which is low density polyethylene. Basically, they're the exact same polymer, except for one is more densely packed together. And the reason it's more densely packed is in the linear picture, I can get these a lot closer together because these long linear chains can be can squish together a little bit more. If things are branched, it's kind of pushing itself apart. I have more gaps. And so if I have a branched polyethylene polymer, it's going to be a lower density than if I have a linear polyethylene polymer. We'll talk about thermal sets really quick. Thermal sets are polymers that once they've solidified, they can't be melted or remolded. There's a lot of cross-linking that happens, and this is where we're going to talk about what cross-linking is. They tend to be brittle. They don't soften with heat. And some examples would be things like tires, structural plastics, or non-recyclable plastics. And again, they're non-recyclable because you can't heat them up and remold them. There are some things you can do. We don't necessarily consider it recycling, but if you want to get rid of it and you want to use it for another purpose instead of just being waste, you could do something like shred it or grind it down and use it for filler somewhere. So what it is let's say I have a polymer chain and another polymer chain that comes into it or comes near it. Instead of them just being attracted with the van der Waals forces, what I can do is I can add some type of catalyst in there. And a lot of times these are epoxies, they're resins, and you add some type of additive to harden it and to cause this reaction to happen. And a lot of times when you use epoxies, they actually get warm, or you can see some type of steamish smoke, something coming off of it. And what's happening is it's actually changing the chemical structure. We're actually forming new covalent bonds. These are covalent bonds, not van der Waals. There are going to still be some van der Waals forces wherever the covalent bonds don't happen, but these are much, much stronger because we have additional covalent bonds, but it also makes them brittle because we can't slide them like we could with the van der Waals. It also means that this is the reason we can't soften them with heat. I can't add some heat and then magically have these new covalent bonds just disappear because I decided to reheat it. Once those covalent bonds are made, they're as strong as the other covalent bonds in my original polymer, and I can't, break just the new bonds and leave the old ones there. This one would be a cross-linked material. And the more cross-linking I get, I end up eventually getting a networked material. And all a network material is one that has a significant number of cross-linking. 100% networked material would look something like this, where I get these polymer chains together and that should look like that. These link together everywhere. It's completely networked together. This part should not be here. So that would be what a complete network material. And so again, the cross-linking are the new covalent bonds that are formed. So if we go back up here, there is little to no cross-linking. It's all van der Waals forces between these polymer chains. And with thermal sets, we do form new bonds, which is why we can't recycle them or remelt them. All right, so now we're going to even move a little bit quicker because there's a lot of information. More than anything, this is just going to show that we have so much going on here, but I'm really not going to spend the time to go into detail on these things. So we have isotactic. Isotactic means that I have a polymer, and my side groups here, I'm going to have one side group that's coming out towards me and one that's going into the screen. One that's coming out and one that's going in, one that's coming out and one that's going in. And what we have is we could have a molecule on one side and let's say a hydrogen on the other, and that pattern continues. And so if I was looking down this molecule, if I was walking down this entire molecule, like the molecule is a path, on one side, I would see all of my R's, and on the other side, I would see all of my H's. That's what isotactic means. Symbiotic, again, I'm going to have something coming in and something coming out on each one of these. But in this case, they're going to flip-flop. I'm going to have an R and an H, and then on this one, it's an H, then an R. R, then H, then H, then R. So if I'm walking down this, I see my R on my right and an H on the left. I take a step to my next one, and it's flip-flopped. It's now an H and an R, and then it's an R and an H. A tactic just means that it is random. I could have an R and an H, I could have an R and an H, then I could have an H and an R. There really is no pattern along it. All right, even more stuff. We have some what we call cis, and cis would look something like this. I would have my molecule coming in, I would have CH2, and it would come together, and let's say that I had this double bonded carbon, and up here I had a CH3. Over here I would have my H, and down here I would continue on with a CH2, and so forth. It might take you a while. You might have to look at this on your own. Again, I'm not getting into all these little things, but I do want to show you these things. I'm going to draw my trans over here, and that is cis. They're on the same side, so these are both on the same side. With trans, it actually jumps sides. So if I draw the same picture, CH2, C, and I kind of have this same picture. I have this double bonded carbon in the middle with these branches coming out, and instead of my polymer chain both being on the same side, it flops. My polymer chain moves over there, and over here I am going to have my CH3, let's say, and my H over here, or whatever it happens to be. They really could be any type of thing attached. But this one, it goes across, and that's trans. All right, now we have even more things that we want to talk about. I could have blocks of, I could look at my my polymers, and I could have kind of a random structure. I could have, let's say that each one of these circles is one of my mers, one of my units of my polymer, right? One of these triangle type shapes up here. So that is the circles. And what I could do is I could have something random where it changes for a while, maybe into a slightly different chemical that's being attached, and then it goes back, and then maybe a little bit more of something else, and it just kind of jumps back and forth between some. It kind of has this random structure. I could have alternating, and alternating I think sounds probably pretty standard. It just alternates between what my mer looks like, what that chemical unit looks like that's bonded together. I could have blocky, and blocky ones are where I have these large swaths of one type of polymer, and it's all attached into one long strand, but maybe for a while I all have one kind, and then I have another kind, and then maybe it goes back, but I have these go in blocks. And lastly, we could talk about the branches again. And what the branches could look like is I could have all my backbone be one chemical structure, and my branches could be a completely different chemical structure. So there's a lot of stuff going on here. Last thing that I wanted to show real quick is I wanted to show how a polymer chain crystallizes and how it's amorphous. If I just even have one polymer chain and it's really, really long, it can fold in on itself. And I'm going to draw this in 2 dimensions, but remember, it lives in a 3-dimensional world. And so if it were to crystallize, I could have these match up, and it might even fold up on itself. And these are really close together, and they will crystallize. Now remember that the way that it's attracted here are van der Waals forces, but they are stacking together. It bends up in on itself. And so if we look at this middle section here, I didn't draw it necessarily super pretty, but you can see how these are stacked together and it has some direction. It's very well oriented. Now in the exact same polymer, it might stop crystallizing and it might start getting kind of crazy and be more amorphous, not have much of a structure at all. And so then it would be more amorphous if it were folding in on itself like this, and then it might start crystallizing again over here. It can really do a lot of things. Polymers are very, very interesting. When we talk about polymers, we usually associate polymers with a molecular weight. A molecular weight, the larger the molecular weight, this tells us something about how long the polymer chains are. So the length of the chain. So the higher the molecular weight, normally the chain gets longer because, well, there's more things there. So the molecule, the polymer chain, will weigh more. This tells us something about the strength of the material. The longer it is, the stronger it is, and the reason for that is you can see that it is really starting to get up and tangle itself. So the strength is related to entanglement. So even if you have the same type of molecule, let's say we're dealing with polyethylene. If I have a longer chain of polyethylene that's being used in my polymer, in my material, that length of the chain is going to make it stronger because it entangles more. But if I'm using short molecules, even if it is the same material, even if it is polyethylene, it's going to be of a less quality, or in other words, it's not going to be as strong. The properties are going to be different because the molecular weight is different and there's less entanglement.